captions in English, please. So this is the 5th video on chapter 12, and it will focus on covalent Lewis structures when electrons are shared between nonmetals. So when nonmetals bond with other nonmetals, a molecular or covalent compound results. So remember how molecular and covalent are synonymous. You can say one or the other. Molecular compounds contain covalent bonds in which electrons are shared between atoms. They are not transferred like in ionic compound. In Lewis theory, we represent covalent bonding by allowing neighboring atoms to share some of their valence electrons in order to attain octets or duets for hydrogens. But most main group elements need octets. So let's look at the video to get an overview before we practice this.
Dots on one side. Lewis diagrams are often used to represent covalent bonding in molecules and ions. In covalent bonding, atoms share valence electrons in order to get a full octet, or duet. That is, every non-metal element wants 8 valence electrons, except for hydrogen, which only wants 2 valence electrons. The simplest molecule possible is that of hydrogen, H2. A hydrogen atom has 1 valence electron, but it wants to have 2. So in order to satisfy its desire for another electron, 2 hydrogen atoms will share their electrons with each other. And the crazy thing is that in the wonderful world of atoms, the shared electrons are counted as owned by both atoms. That means that both hydrogen atoms are happy because they both satisfy the octet rule. Now, we normally draw hydrogen and other molecules like this with lines to represent shared electrons and dots only for non-bonding electrons. These two diagrams of a hydrogen molecule are equivalent because one line, which is a single bond, represents 2 shared electrons. In the same way, 2 lines between atoms would be a double bond and would be the sharing of 4 electrons. An example of a molecule with a double bond is oxygen, which looks like this. Notice that in this Lewis diagram, both oxygen atoms have 8 valence electrons, 4 from the double bond and 4 from the lone pairs of electrons. By the way, 2 dots together are called a lone pair of electrons. Some molecules contain triple bonds, which we write using 3 lines that represent the sharing of 6 electrons. An example of a molecule with a triple bond is nitrogen, which looks like this. Once again, notice that both nitrogen atoms have 8 valence electrons. 6 from the triple bond and 2 from the lone pair of electrons. Okay, how do you actually draw the Lewis diagram of a molecule? Let's start with water, H2O. There are 5 important steps that you need to follow when drawing the Lewis diagram of a molecule. First, count all of the valence electrons in the molecule. For water, each hydrogen has 1 electron, and we multiply that by 2 because there are 2 hydrogens in the molecule. The oxygen has 6 valence electrons. Add those all up, and we have a total of 8 valence electrons for the water molecule. Step 2. Determine the central atom. The central atom is the one that all the other atoms will be bonded to. It is usually the element that there is only one of. In the case of H2O, because there are 2 hydrogens and only 1 oxygen, we choose oxygen as the central atom and write it in the middle. Step 3. Draw single bonds to the central atom. Step 4. Put all of the remaining valence electrons on atoms as lone pairs. For H2O, we start with 8 valence electrons. We have used 4 electrons for the 2 single bonds, so that leaves 4 more electrons left over. We put all 4 of these remaining electrons on oxygen instead of hydrogen because hydrogen is already happy with 2 valence electrons. Remember, never give hydrogen more than 2 valence electrons. Everyone else wants 8 valence electrons, but hydrogen only wants 2. Step 5. Turn lone pairs into double or triple bonds to give every atom an octet or duet for hydrogen. Pause the video and see if all the atoms in our H2O are happy. Because each hydrogen has 2 electrons and the oxygen has 8 electrons, everyone is happy, and there is no need for double or triple bonds, which means that our Lewis diagram of water is now complete. Alright, let's try one more example just to make sure that we've got this. Draw the Lewis diagram of sulfur trioxide. Once again, the first step is to count all the valence electrons. There is one sulfur with 6 valence electrons, and there are 3 oxygens with 6 valence electrons each. 6 times 3 gives us 18 valence electrons for the 3 oxygens. The total would be 6 plus 18, which equals 24 valence electrons. Step 2. Determine the central atom. This time, sulfur is the central atom because there is only one sulfur in the molecule. We write sulfur in the middle with the 3 oxygen atoms all around it. Step 3. Draw single bonds to the central atom. Step 4. We started with 24 valence electrons, and we have used 6 electrons to make the 3 single bonds. This means that we have 24 minus 6, or 18 valence electrons remaining. We now put those remaining 18 valence electrons on atoms as lone pairs. Count by 2s when adding them. 2, 4, 6, 8, 10, 12, 14, 16, and 18 valence electrons. That's it. We've now used up all of our valence electrons. Step 5. First pause the video and check to see if any atom does not have an octet or duet. That's right, the sulfur is unhappy because it only has 6 valence electrons. So what can we do to make it happy? We cannot just give it more electrons since we don't have any more. Instead, one of the oxygen atoms can take one of its lone pairs and share those 2 electrons with sulfur in another bond. The double bond between oxygen and sulfur now makes every atom happy with 8 valence electrons. Be sure to follow these steps when drawing Lewis diagrams. Thanks for...
So, let's look at the Lewis structure of water again. So when you look at the Lewis symbols of just hydrogen and oxygen by themselves, they have so hydrogen 1 dot for 1 valence electron and oxygen 6 dots for 6 valence electrons. And so in water, hydrogen and oxygen share their electrons so that each hydrogen atom gets a duet and the oxygen atom gets an octet. So by putting 2 hydrogens around oxygen, the 2 hydrogens share their 1 valence electrons with oxygen. So that completes the octet for oxygen, and now it has 8 valence electrons around it. And the hydrogens are an exception. They only need a duet. So by sharing with oxygen, they get a duet. Because they have a single bond with oxygen there. So let's make sure the vocabulary is done. Electrons that are shared between 2 atoms are called bonding pairs. So we call these bonding pairs. Electrons that are only on 1 atom are called lone pairs, or sometimes non-bonding electrons. But lone pairs is easier to say, so I will always use lone pairs for non-bonding electrons. So bonding pair electrons are often represented by dashes to emphasize that they are a chemical bond. And I prefer that you do this representation with the dashes over the ones with the dots. Okay. Remember that each dash represents a pair of shared electrons, not just it's 2 electrons in there for every line. Okay, so we'll go over the steps for drawing Lewis structures again, and I will add some comments. So the first step when you need to draw the Lewis structure of a molecule is to determine the total number of valence electrons for the entire molecule. So if you have a polyatomic ion, it's those ions that are, they are ions overall, but the atoms are bonded by covalent bonds within the polyatomic ion. And so they are strong bonds and they stay as a unit. They move around as a unit. So you will add or subtract the appropriate number of electrons to the total. So if you have a polyatomic ion, you need to remove an electron if it's a cation, a positive ion, and add an electron if it's a negative ion. And for each negative charge, you will add an electron. So let's say it's a CO3 negative 2, you would add 2 electrons to the total of valence electrons from the atoms. Determine the central atom and position the atoms, find the arrangement. The central atom is generally the least electronegative element. So typically the most metallic one. So there's different ways of seeing that. The least electronegative or the most metallic one. The central atom will never be hydrogen or an halogen. There are some exceptions, but I will not expect an exception from you. The halogens will be terminal atoms, like the hydrogen, which means they will be on the outside of the molecule. They will not be in centrals. If there are multiple atoms of the same type, then generally the single atom will be the center. So then next you put all the other atoms around the central atom with a pair of electrons in between each of the atoms. So basically you put single bonds between the central atom and the atoms around it. Next, you calculate the remaining number of electrons, and with the rest of these electrons, you will start completing octet. And by doing this, you will give lone pairs to the outside atoms first and working your way to the central atom. Remember that no atoms should have more than an octet, so 8 electrons maximum around a given atom. And hydrogen should only have 2 electrons. It's an exception. There are other exceptions with beryllium and boron, we'll see later on. Next, you want to check that all the atoms are satisfied, which means here we want to make sure they all have an octet. So except for hydrogen, we want it to have a duet, so 2 electrons, beryllium 4 electrons, boron 6 electrons, and others 8 electrons. If after adding all the additional electrons you have atoms that are not satisfied, then you move the electrons to form double or triple bond. And then if you have only used dots up to that point, you need to put lines to show the bonds. So a single line for a single bond, a double line for a double bond, and a triple line for a triple bond. And then you need to do a final check to make sure that the total number of valence electrons is still correct, because sometimes that may change in between, and this will be wrong. You need the total number of valence electrons to be the one you calculated at the beginning. So let's practice by doing the Lewis structure of NH3. So because you have no experience doing this, you can watch, but you can also try to do it. So pause the video, try to do it, and then check. So the first step is to determine the total number of valence electrons in NH3. So we have nitrogen from group 5A. There is only one nitrogen in the formula. And nitrogen has 5 valence electrons being in group 5A. And so that's 5 electrons from nitrogen. Hydrogens, group 1A, has 1 valence electron, but there are 3 hydrogens. So that's going to be 3 electrons from the 3 hydrogens. So the total number of valence electrons for NH3 is 8. Next, you need to determine the arrangement of the atoms. And so here you have N and then 3 hydrogens. When you have a formula like that, you put the single atom in the center and the 3 hydrogens around it. Another way to see this is that nitrogen, well, it's actually not the least electronegative, but typically hydrogens, we have said earlier that it cannot be a central atom, so that really rules out the fact that you would put it as the central atom. So like this, N, and then surround nitrogen on 3 sides by hydrogen. Next, you want to attach each bonded atom to the central atom with a pair of electrons. Then you want to place the remaining electrons as lone pairs or multiple bonds to complete the octets. So here we need to calculate how many electrons we have left. We started with 8, a total of 8. We used 6 with those 3 single bonds. So that's 2 electrons remaining. So those 2 electrons need to be put down as a lone pair. Remember how hydrogen cannot accommodate more than 2 electrons, and so those hydrogens are already satisfied. So the lone pair will go on nitrogen because nitrogen has only 6 electrons around it. So you will complete the octet for the nitrogen atom by giving it a lone pair. And so finally you want to change those pairs of electrons as single bonds, so as lines between the nitrogen and each hydrogen. So as I said earlier, I prefer that you finish with the structure on the right. I don't really like the structures on the left. So that would be the final Lewis structures for nitrogen. Let's check that the total number of valence electrons is correct. So we have 3 single bonds times 2 electrons each. So that's 6 from those single bonds, and then 2 electrons in the lone pair. That's a total of 8 valence electrons, which is the number we need. Let's draw the Lewis structure for carbon tetrachloride, CCl4. So first step is to determine the total number of valence electrons. So we have carbon, group 4A, has 4 valence electrons. There is only 1 carbon in the formula, so that's 4 electrons from carbon. Chlorine, group 7A, has 7 valence electrons. Times 4 chlorine, there is 4 chlorine, so 4 times 7 is 28 electrons from the 4 chlorines. And that gives us a total number of valence electrons for CCl4 of 32 electrons. Second step, determine the arrangement of the atoms. And here, whenever you have carbon, put it in the center. It's really an atom that will always be in the center. And here you see carbon is less electronegative than chlorine, or is more metallic than chlorine, being more on the left side of the, chlorine. So put carbon in the middle, and because you have 4 sides around carbon, you can give each side a chlorine. So it will look like this. Carbon in the center, and then chlorine on the 4 sides, like that. So the next step is to attach the chlorines to the central atom, so to carbon, give a single bond between the carbon and each chlorine. Then place the remaining electrons using lone pairs or multiple bonds. And so we need to calculate the number of electrons remaining. We started with, how many was it? I forgot. 32. We started with 32 valence electrons, minus 8 electrons that we just used to make the single bonds. So that's 24 electrons remaining. So 24 electrons that we will use as lone pairs on the chlorines, right? Because you start giving the lone pairs on the outside atoms first. So each chlorine will get 3 lone pairs, right? If you give 3 lone pairs to each chlorine, they will have those 6 electrons as lone pairs plus 2 electrons for the single bond. And so that's going to give an octet to each chlorine. And then all the chlorines have octets. And then carbon also has an octet by having 4 single bonds. 4 single bonds times 2 electrons each, that's 8 electrons around carbon. So carbon also has an octet, just like every chlorine. So all atoms are satisfied. So now let's verify that we have 32 electrons, 32 valence electrons total. So you count 4 single bonds times 2 electrons each. It's 8 electrons. 8 plus 6 electrons on each chlorine. So 8 plus 6 is 14, plus 6 is 20, plus 6, 26, plus 6 is 32. So we do have our 32 valence electrons in total. So that's the correct structure for CCl4. Let's do the Lewis structure for CS2. So start by determining the total number of valence electrons in the structure. And here we have carbon, group 4A, has 4 valence electrons. There is 1 carbon, so it's 4 electrons from the carbon. Sulfur, S is sulfur, in group 6A, has 6 valence electrons. But there is 2 sulfurs, so we need to do 2 sulfurs times 6 electrons each. That's 12 electrons from the sulfurs. And 12 plus 4, it's 16 electrons for the CS2 molecule. Next, you want to determine the arrangement of the atoms. And so here again, when you have CS2, the first atom in the formula, and if it's a single one, typically is in the center. And as I said with the carbon tetrachloride, carbon is always in the center. So put carbon in the center, and this time only 2 sides will be occupied by the sulfur. So carbon surrounded on each side by a sulfur. Next, attach each bonded atoms to the central atom with a pair of electrons. So put 2 electrons between between carbon and each sulfur. And finally, place the remaining electrons using lone pairs or multiple bonds to complete the octet. So we had 16 valence electrons to start with, and we used 4 electrons by doing those 2 single bonds. So that's 12 electrons remaining. So 12 electrons that will be used to do lone pairs on the sulfur first. So each sulfur needs 6 electrons, so 3 lone pairs each, so that they get an octet, right? When you put 3 lone pairs on each sulfur, that's 6 electrons plus the 2 from the single bond between sulfur and carbon. That's going to be 8 around each sulfur. So this way the sulfurs have their octets. And we have used all the electrons, right? The remaining 12 electrons are placed as 6 lone pairs of electrons on both sulfurs. However, this does not complete the octet for the carbon. You see that carbon is surrounded by only 4 electrons. But we cannot bring more electrons because we've used them all. If you look at the structures, we have 8 and 8 is 16 total. So you cannot bring more electrons. And so when you have this problem of having the central atom not being satisfied, you need to share lone pairs. So the sulfurs will have to share a lone pair, and each of them, because carbon has only 4 electrons right now, it needs 8. So each sulfur will have to share a lone pair. And so it will look like this. You show that a lone pair will be shared from each sulfur. So then there will be not only 2, but 4 electrons between the carbon and each sulfur. So 4 electrons on the left, 4 electrons on the right of carbon. And as I said, I don't want you to leave it like this with dots. I want you to make a double line for a double bond. So you write 2 lines between each carbon and sulfur, and that will make double bonds. And so this way, carbon is surrounded by 8 valence electrons. If you look at carbon, there is 4 electrons on one side and 4 electrons on the other side. So it's a total of 8 around carbon. So it gets its octet. And the sulfurs, they still have their octet because they have 4 electrons, shared with carbon, plus 4 electrons from the 2 lone pairs. So each sulfur also has an octet. So we have octets for all 3 atoms here. And let's check finally that the total number of valence electrons is the 16 we had at the beginning. So we have 2 double bonds. So each double bond is 4 electrons. 4 electrons times 2, it's 8. Then plus 4 on a sulfur, that's 12, plus 4 on the other sulfur, and that's 16. So we do have our 16 valence electrons, and that's the correct structure for CS2.